Good afternoon, everyone. I'm Vignesh, second year EC student at EC department student at NIT Trichy. Today, I'm going to explain about my assignment with for transmission lines and wavegates ECPC 16 course. Our project is based on a multi-band impedance matching for dynamic RF systems using machine learning, which will be implemented on STM32 H7 microcontroller. So I will go through the project one by one with the comparisons and the problem which we overcome and the next things which we can do on the project. First, let me start with the motivation and problem statement. The previous H16 problems with the impedance matching was uh, the single band limitation. So it was just tuning for only one 2.5 gigahertz or some 5 gigahertz. But what we have done is we have created multi-band like 2.4 gigahertz, 900 hertz, and 5.8 gigahertz. Our ML model trained for with multiple inputs so that it can uh, do the adaptivity for everything. And the previous issues which were there in most of the papers like Jayang et al. Or other papers which are compared was the minimum time it took itself was 25 milliseconds, which was less in most of the cases, which was not adequate enough for rapidly changing environments like mobile IoT. So we have decided to come up with a new thing like implementing in a microcontroller with a fast ML TensorFlow Lite model, which will do it in a less than 10 seconds or at least a 20 milliseconds. The third one was high power consumption, which was also there in all of the most of the ML enhanced models. Because in ML enhanced models, the power consumption will be very high. They will be using high power systems mostly. So we have did the thing based on TensorFlow Lite, which is edge friendly power budget inference control like below 50 millivolts only it will take. So it will for longer life. So battery issue won't be a problem compared to the previous versions, and it is much better to do that. So these are the problem statement and the ideas we have took to overcome that. I will explain one by one how the ML model is trained and the data set which we have created for that through the particular presentation in further time. So yeah, so proposed system architecture, hardware and ML integration. So if an ML model or the microcontroller needs to work, it needs to get the inputs. So our first input was like input or the output. Like I will tell about both of things. So the input features of our ML model is like the reflection coefficients of all the three bands 2.4 gigahertz, 5 gigahertz, and 900 hertz, which you have said, and the temperature and the humidity. So temperature and humidity also plays a major role in the values of the impedance matching. So we have included that as well. So the matching networks is based on switched capacitor array and vector diode, which is mentioned in the slides. So based on our ML model output, these things gets changed rapidly. So the matched impedance signal is to the antenna load. The output will be changed in the antenna load, and the sensing model which we are using is basically the directional coupler and the RF detector value to measure the reflection coefficients. So these sensing model will check the values and then give it to the ML model, and then ML model will predict and then change the vector diodes and capaciting modules. So this goes like a feedback and which gets updated in a few very few milliseconds, and then this is the one of the fast proposed systems which we have known by the comparisons. So the five features are three reflection bands are three reflection coefficients are three bands, temperature and humidity, which we have generated synthetic data set, which I'll say about in the next slide. So the data generation approach. So as we can also generate the environmental simulation using CTS and other environmental tools, ADS or HFFS, but we have gone through a synthetic data set generation as environmental or other simulation makes a lot of domain head space and computational effort with a lot of data need to be generated over time. So we have used a synthetic data generation for this purpose, which also works well, but we need a lot of tuning over in the further time. So we have did that, and the machine learning model was based on the previous other comparisons using the both LSTMs and convolutional neural network, which was a hybrid thing which we have developed. So with this idea, what we are doing is we are doing a temporal learning through the LSTMs and the spatial learning through the convolutional neural network, which is generally used for the images. So this is a hybrid model which acts well. The vector diode voltages are basically in a regression, and the switch capacitor values are basically like a classification on or off like that. So the main thing which I did in this one was TensorFlow Lite version which you have used. So that is for the quantization of to the 8-bit quantizing of the model. They have also quantized to 8-bit precision to reduce the size of the model and to deploy on embedded device. TensorFlow Lite basically makes it to be easier to run on a embedded device. Basically STM32 which is the preferred one for the 480 megahertz which it possesses. So yeah, that is the thing. And yeah, target goals was less than 10 millisecond and the power of less than 50 millivolts, and the reflection coefficient, like reflection, was less than 0.1. These are the equations which I have used to create everything. The ML equations and the transmission lines equation which I have used.
So yeah, I'll speak about the difference between the similar projects existing on the internet and our project. First one is our project runs on a very low power device. Like it runs on a microcontroller called STM32, and which consumes very less power. And the next thing is our model works. We are trained data on various different frequency ranges. So the tuning works on multiple frequency bands, not just generic 2.4 gigahertz, not just one particular band. It works across multiple bands. And if you see this paper on released in 2019, they use a very high-powered ML model, which is slightly harder to implement it in STM32, and it's also very slow since it's very computational due to its computational overhead. And the same thing goes here. They use a very generic algorithm, which is not very good to run on low-powered hardware. And the same thing goes for all of them. They either run on a one particular frequency band, or they consume way too much power. Which consuming way too much power is not a good thing in IoT and other related low power electronics, which are actually being integrated into smartwatches and mobile phones, etc. And what other thing we are planning to do is, like, if we are planning to improve things further, what we can do is we can implement something called a federated learning system, in which we'll have a central server which will gather data from a lot of smaller servers. A smaller server is probably the local system that we'll be running, and it will collect data from there and then do a very minimal computation in that server, the local server, and get all the data and send it back to the huge server. And the major computation happens here, and the computation with the data we use is not raw data because it's processed. So you're not losing your privacy in any way, and you still get that computational benefits as well. And this will happen if, like, if there is a network of such devices connected, and now it's not the case, so we do not go for it. And we can also try to reduce the size, like, or even better, we can try to implement it in a smaller, less power consuming hardware, which brings it much closer to, like, actually building usable electronics of it.